Concrete is incredibly strong under compression, which makes it the standard material for heavy-duty floors. But this strength comes with a heavy penalty: sheer, inefficient dead weight. The thicker a traditional slab needs to be to support a heavy load or span a large gap, the more heavy concrete you have to pour just to support the weight of the slab itself. To stop adding weight to support weight, engineers use a technique called a bubble deck slab. This method physically eliminates unnecessary material from the floor while retaining the same structural integrity. This 3D diagram shows how it works. Instead of a solid block, the interior features a uniform grid of hollow spheres sandwiched between steel mesh. The system relies on three basic materials: recycled plastic spheres, standard steel rebar, and ordinary Portland cement. By combining these three elements to displace the heaviest part of the concrete, builders lower material costs and environmental impact, all while maintaining the exact same load-bearing capacity as a solid slab. Let's walk through how it is built. We start our installation plan with this top-down blueprint. The total floor area is divided into sections, typically measured out as modular panels up to 3 meters wide. Within each of these defined sections, crews lay down an initial 60mm precast concrete base. This forms the absolute bottom of the slab. Directly on top of that precast base layer, a bottom grid of steel rebar mesh is laid out. Next, diagonal steel lattice girders are installed upright, resting directly on the bottom mesh. These upright girders act as the locking skeleton of the slab. They are specifically designed to hold the plastic voids perfectly in position, keeping them spaced accurately. Mapping out and installing this precise steel framework early dictates the structural alignment of the entire floor system, well before any major weight is added to the building. Now, the high-density polyethylene hollow balls are placed between the steel lattice girders. They drop directly into the pockets created by the steel framework. This cross-section shows the physics. When a slab bends under a load, stress vectors concentrate at the top in compression and the bottom in tension. The concrete in the middle section bears almost zero structural load. It is essentially dead weight. Because that middle concrete does nothing, the hollow plastic spheres displace it. To lock them in, the top layer of steel rebar mesh is laid directly over the newly placed spheres. This creates a critical construction checkpoint. The top mesh must be tightly bound down to the bottom girders. Warning tone. If the mesh is left unsecured, the lightweight plastic balls will act like buoys when the wet concrete is poured. They will forcibly float to the surface, displacing the top steel and destroying the structural integrity of the slab. But when correctly tied down, this tightly secured sandwich of steel and plastic converts a useless interior dead zone into a highly stable, lightweight core. At this stage, we have completed modular panels, but they are individual pieces. The seams where these 3-meter panels meet represent a major structural vulnerability. To fix this, crews perform a process called stitching. They place loose steel reinforcement bars across the physical gaps, physically tying the distinct panels together. Failing to stitch these panels leaves you with isolated, weak sections that will easily crack under stress, rather than a continuous, load-bearing floor. Once stitched, it is time for the pour. The required mixture for a bubble deck is specific. You must use standard Portland cement with 3/4-inch aggregate, and you strictly avoid adding any chemical plasticizers. This precise mixture is continuously poured over the completed steel and bubble matrix. The wet concrete must flow completely underneath the plastic spheres so that it fully encases the bottom steel mesh, leaving no air gaps below the structure. The combination of properly sized aggregate and an uninterrupted flow ensures the concrete integrates with the steel and plastic, creating a unified, load-bearing structural unit. Once the pouring is finished, the slab is left to cure. From the outside, the finished product looks identical to a traditional solid concrete floor. Let's look at this side-by-side volume comparison. On the left is a standard solid concrete slab, and on the right is our cured bubble deck slab. You can clearly see the exact 35% volume of concrete missing from the center of the structure. Those interior void spaces eliminate a full third of the structural concrete normally required. That reduction in material translates directly to a drastically lower dead weight for the entire building. By analyzing how a slab handles tension and compression, engineers figured out how to remove heavy material exactly where it isn't needed. This approach turns a massive structural liability into a more efficient and sustainable floor system.